Hi everyone, welcome back to Mind Over Math. This is part 3 of a series in limits. There's also a part 4 to follow. So here's some rules for unbounded. The first is what we just did. The left and the right limits do not agree, so it's a does not exist. I call that DUI because of the test of whether or not you've been driving under the influence. You have to put your finger on your nose and your left hand finger on your nose, and if one hits your forehead and one hits your chin, you're going to have a DUI. So those are DNEs. Number 2 here we just did several examples of unbounded from the left and the right, typically a vertical asymptote. And the last one we didn't do, and you can do that on your own, it's called an oscillation. And this is an example of that. Put your graphing calculator into radians and do the sine of 1 over x. That'll be an example of an oscillation. And also, without spending a great deal of time, I want to state the limit rules, the limit operations, when f of x has a limit of L and g of x has the limit of m. We can follow the add and subtract rule here, the multiply rule, the divide rule, and the power rule. So I won't go into those, but those are the rules of operations that they operate limits by. Last thing I want to do is a comparison of 3 graphs to emphasize limits. As we find out on this one, it's all done. If you plug in the 1, substitute it in for x, you get 2. And really this is just a straight line graph with an intercept of 1 and a slope of 2. And this point, 1, 2, is just a point on the line. As you approach from the left or the right, the limit is 2. A second one that we want to do also approaches, x approaches 1. This one's a little more complicated. When I plug 1 in, I don't get a nice number like 2. I get 0 over 0, which is the indeterminate form. This indicates the problem needs to be reduced. In our case, we can see it needs to be reduced by factoring. So we factor x squared minus 1 into x plus 1, x minus 1. And notice that this cancels. This sometimes is called a curable. You can cancel this, and you get x plus 1. And now you come back. You took a little detour after the determining was indeterminate. You reduced it. Now you get back on track and you plug in the 1 again and you get 2. So this is the same straight line the other one was. The difference is this point 1 was in the original problem, was in the denominator. It was not canceled out yet. That means the denominator cannot be a 1. So we would say this is a curable in that this is a x equals 1, 2 is a hole in the graph. As you're drawing it, you actually lift your pencil, go on the other side of 1, and continue the drawing up to the right here. So draw, lift your pencil, draw again. Another comparison, much more complicated as it looks, is this function. It's a cubic over squared, x towards 1. Plug in the 1, you get 0 over 0 again. That means it's indeterminate. That means it reduces. So let's reduce it. You may remember how to reduce 4 terms. You group by 2's, and greatest common factor in the first group is x squared, and the greatest common factor in the second group is negative 1. The denominator also factors nicely. You'll notice here the way the numerator is rewritten is x squared minus 1 times x minus 2. You'll notice the denominator has the x minus 2, and those cancel. That's a curable. You'll also notice that the x squared minus 1 will factor even more, and the remaining denominator, x minus 1, is going to cancel with that, and I end up with x minus 1 equals 2. And this is the same one we had before. So here's the line, x minus 1 equals 2. Okay, we got that moved out of the way. So this turns into x plus 1 equals 2, which is the same as we had a while ago. Now you'll notice here, because we canceled x minus 1, which actually was a part of the original denominator, even though it canceled, we put in that place a hole in the graph. And we also had an x minus 2, which is x equals 2, where there was a hole in the graph also. Now, if these had not canceled out, they did cancel out. When they do cancel out, you just put a hole in the graph. When they don't cancel out, you put a vertical asymptote in their way. A vertical asymptote means it totally changes the graph. Okay, so the last one we're going to do is a graph that is piecewise defined. You'll notice that at y equals negative 2 is this graph right here. Y equals 1 is this graph here. Y equals 3 is this graph here. But you'll notice these don't go on forever. They're just limited. Think of the time of the day from negative 4 to negative 2, and then they're done. And then the second one starts at negative 1 but doesn't include it, and goes to 2, that's this one, negative 1 open to 2 closed, and then we go from y equals 3 up here, from 2, doesn't include 2, it's open, to 5, which is closed. So I'm going to put these as limits. I'm not going to rewrite f of x every time because it's too much work, but I do want to approach it from the negative 1 left side. So you'll notice I drew a line, this is not an asymptote, where x equals negative 1, and on the left side, the only thing that exists is this one at negative 2. Right there. Now, when I put it negative 1 from the positive side, the only place that exists is right in here. This graph isn't there. This graph isn't there, just this one. So the limit, the y direction, is 1. And then if I go from both sides, negative 2 and also positive 1, well, we don't agree on the limit. That is a DNE, does not exist. Let's do that with positive 2 over here. X equals positive 2 would be a line right there. From the left side, the only thing that exists is this one. So that answer is 1. And from right of 2, this is positive 2 here, this one exists, only this one. None of these exist over there. And so as we approach from the right, going this direction, see we're going from the right, we're going this direction, towards 2, we expect the limit to be 3. From both sides of 2, we expect the limit to not exist, DNE. So this is an example, part 2 of limits. Some of the limit operations were in there. Some good examples of unbounded, where we go to positive and negative infinity. And here where we have the broken stair-step graph and left and right side behavior. Hope this helps you. This is part 2. You did it. You made it through 3 parts. There's one more part to follow. Don't miss it. A study tip: take some screenshots of the main ideas and formulas and summaries throughout all these videos, but then study them. In the upper right-hand corner, make sure you subscribe. In the upper left-hand corner, make sure you check out other videos. Likes are below, and make comments on topics you need.